Your vector database decision might already be hiding inside Postgres. If your app needs semantic search, keyword search, tenant filters, auth, backups, joins, and boring operational safety, the question is no longer, should I use a vector database or a relational database? The better question is, how far can one Postgres system carry the retrieval layer before a dedicated vector service is actually justified? In this video, we will build the mental model for a Postgres 18-era pgvector stack. One table for documents, one vector index for semantic recall, one full text path for lexical precision, and one SQL ranking layer that fuses the two. Start with the product requirement. A user asks a question. The app retrieves candidate passages. The LLM answers with citations. That sounds simple, but production search usually carries more constraints than a demo notebook admits. You need tenant isolation. You need deletion rules. You need document freshness. You need exact metadata filters. You need backup and restore. You need migrations. You need observability. That is why Postgres keeps showing up in RAG stacks. pgvector gives you approximate nearest neighbor search inside the same database that already stores the rest of the product state. Here is the smallest useful schema. A documents table stores the tenant ID, source URI, body text, timestamps, a generated text search vector, and an embedding column. You add a B-tree index for tenant and freshness filters. You add a GIN index for full text search. You add an HNSW index for vector similarity. The point is not to make every query hit every index. The point is to give the planner and your retrieval code 3 clean levers. Metadata filters narrow the legal row set, full text search catches names and exact terms, and vector search catches semantic similarity. The ingest path has 4 steps. First, normalize the source document. Second, chunk it into passages that match your answer style. Third, embed each chunk. Fourth, insert in batches and let Postgres build or maintain the indexes. For small systems, insert as you go. For a larger backfill, batch hard. Use copy, keep transactions sized so they do not hold locks forever, and build large indexes after the bulk load when possible. The detail that matters most is provenance. Store source URI, source version, updated timestamp, chunk ordinal, and deletion state. At query time, run 2 searches. The vector branch asks, which chunks are semantically close to this question? The text branch asks, which chunks contain the exact names, product terms, IDs, or error strings the user typed? Then combine them. A common pattern is reciprocal rank fusion. Instead of pretending vector distance and text score live on the same scale, rank each branch independently and reward documents that appear high in either list. This avoids 2 common misses: vector search missing exact identifiers, and keyword search missing paraphrases. Here is the trap. Approximate vector indexes are allowed to inspect only part of the index. If your query has a selective filter, the index may find semantically close candidates that later get filtered out. The result can be fewer rows than expected or weaker recall than your offline test suggested. pgvector documents this directly. Filtering conditions can reduce results, and enabling iterative index scans can help address that. The production habit is test filtered recall, not just unfiltered recall. Compare approximate search against exact search on a sample and log how many candidates survive the filter. pgvector also supports binary quantization through expression indexes. The pattern is to search a compact binary representation first, then re-rank the candidate set against the original full precision vectors. The compact index is a candidate generator, not the final judge. You ask it for a broad shortlist, then use the original vectors to sort the shortlist. That gives you a useful memory and speed lever while keeping answer quality measurable. Do not deploy this blind. Measure recall against an exact baseline, especially on the specific embedding model and corpus shape you use. Before you call a Postgres vector stack production ready, walk through the boring list. Monitor query latency by branch, vector, full text, fusion, and final LLM answer. Track candidate counts before and after filters. Store source freshness and document version in the result set. Compare approximate retrieval against exact retrieval on a scheduled sample. Record embedding model version and dimensions. Keep migrations reversible. Benchmark with tenant filters turned on. SQL makes the system look simple. Operational discipline is what keeps it simple. Use Postgres plus pgvector when your retrieval layer is tightly coupled to product data. Metadata filters are central, team familiarity matters, and operational simplicity beats specialized scale. It is a strong default for internal tools, SaaS copilots, support search, policy search, and moderate-sized RAG systems where joins and filters matter. Reach for a dedicated vector database when vector search is the product, index scale dwarfs relational state, you need specialized distributed nearest neighbor behavior, or your recall and latency targets cannot be met inside one Postgres topology. The best Postgres vector design is not trying to cosplay as a separate vector database. It is using Postgres strengths, transactions, filters, full text search, joins, backups, mature operations, and clear SQL ranking. pgvector adds the semantic retrieval path. Postgres 18 improves the platform underneath it. If you remember one thing from this build, remember this: hybrid search is not vector plus keyword glued together. It is eligibility, recall, ranking, freshness, and observability in one retrieval contract. Subscribe to AmTalk Soft for more practical AI infrastructure breakdowns.